Hello, my name is Dr. Kimberly Harrison, and I work with Fitzgerald, a MEMS design firm located here in the Bay Area. And as Dale mentioned, I'll be sharing the floor with Robert Rodriguez of dpiX, which is a semiconductor foundry specializing in glass and flexible substrates. And today we're going to be talking about expanding the world of MEMS through flat panel substrates, flat panel fabs. And even though Robert and I work at different companies that offer very different services, we recognized a lot of common ground recently in terms of mid to high volume manufacturing of MEMS devices. And we thought it would stimulate some really interesting conversation to bring together two sides of this topic in the same talk, the MEMS side and the flat panel side. So in part one of this talk, I'll present my perspective as a MEMS engineer, process engineer, and Robert will give his perspective as a flat panel process engineer. So let's start with the MEMS perspective. A little more about me. I work at Fitzgerald, which was founded in 2003 as a MEMS design and fab house that services the full life cycle of the MEMS product, starting with strategy and design through process integration and prototyping, to foundry transfer and package and test. And over the years, we've developed a robust approach to helping our clients develop their products from concept to commercialization, and you can read more about it in the book published by my colleagues called MEMS Product Development last year. And one of them is sitting in the audience right now. But I wanted to focus today on our approach to helping our clients move towards higher volume manufacturing. So when our clients are ready for higher volume manufacturing, we suggest that they look at a few different issues. Can the foundry perform the necessary process steps to fabricate the device? Does the foundry have the necessary end market certifications? And which foundry can provide the best unit cost at volume to meet business needs? And this is what brought me to look more closely at flat panel fabrication. For some MEMS designs, flat panel fabrication can offer very competitive unit costs and production volumes. What do I mean by competitive? So based on some of our work with clients and foundry partners, I crunched some numbers to look at how a flat panel process would compare with silicon and roll-to-roll processing in terms of cost and manufacturing volume. So in this graph, I'm showing some data, looking at cost as dollars per millimeter squared, so roughly cost per area, and manufacturing volume as the equivalent number of 200 millimeter silicon wafers per year, just as a metric of volume. And what I found was that a 4.5 gen fab like dpiX falls right in between silicon and roll-to-roll processing, which fills a gap that could be of interest to some MEMS device designers who are looking for higher volume and lower cost than potentially silicon can offer, but are not ready to commit to a roll-to-roll process. But I do want to say that not all MEMS devices are compatible with flat panel processing. So looking historically at some products that involved a MEMS device fabricated on flat panel products, I saw many examples of products that were focused on the display market, and I've listed a couple of them here. These products had some really interesting technical and economic advantages over their LCD counterparts by adding some mechanical structures. And it makes sense that I saw a lot of examples of display-related products because flat panel fabs already know how to make displays, and adding a MEMS component seems like a logical progression. But I started to wonder what other sorts of MEMS devices could benefit from a flat panel fabrication, not necessarily the display aspect, but just for the substrate. So I looked a little bit closer at the commonalities between the process capabilities for a MEMS foundry and for a flat panel foundry. And I saw a lot of similar materials. For instance, mechanical and release layers could be made of amorphous silicon, molybdenum, aluminum, silicon oxide, or other dielectrics, or even the panel glass itself. And these are common materials that are found in flat panel fabs. Generally, in flat panel fabs, the layer thicknesses are less than 2 microns, and the critical dimensions are greater than 3 microns. But this does encompass quite a number of MEMS devices. So to further assess which types of devices could be compatible with flat panel fabrication, I looked through some literature, some academic papers, some white papers, to try to see what's been done. And I found a surprisingly long list of devices that have been fabricated on glass wafers, some of which I've listed here. The ones that I saw might not be compatible with flat panel processing are devices that would require a high quality single crystal silicon device layer, such as high Q resonators or gyroscopes. Similarly, devices that need high profile structures that might require a deep silicon etch, such as comb drive actuators, might not be compatible with flat panel processing. And there are some other considerations. So if I approach a flat panel fab with a MEMS project, then I might need to analyze some of their films and processes for attributes that are important to me as a MEMS designer, but not necessarily for the flat panel fab that's making displays. For instance, I might need to determine mechanical properties of their films, Young's modulus, yield strength, density, et cetera, and process geometries such as sidewall angles and edge profiles, surface roughness, et cetera. I will also need to pay attention to how the panels move through the process line at the flat panel fab. There are some parts of the process that could damage delicate mechanical structures. For instance, the robotic handling could introduce large accelerations. I've seen these robots pick up a giant sheet of glass and just wave it around. And it's really scary, but it could introduce accelerations that damage your device. These panels are also generally quite large, about 2 by 3 feet, and there's some sag. There's going to be sagging of the panels. And these could introduce stresses that affect your structures. And jet sprays that are used for wet processing, such as rinsing or etching, might also damage your structures. And then also, flat panel fabs might not have standard MEMS backend processes that we would otherwise expect in a MEMS foundry, such as grind and polish, bonding, die level dicing, and release etch. However, flat panel fabs generally have the ability to cut their panels down into smaller sizes and could deliver the panels in wafer size subpanels that could be sent for further back-end processing. And in that way, we can utilize existing semiconductor supply chains. So that seems like a long list of concerns, but from my perspective as a MEMS engineer, I am accustomed to doing these sorts of risk assessments and figuring out whether a flat panel fab is right sort of depends on the individual product. And in terms of the potential advantages, glass panel fabrication can offer an intermediate option for high volume MEMS processing compared to silicon and roll-to-roll. Historically, products that have MEMS on glass focused on display markets, but if we look more closely at the overlap in process capabilities, a lot of the existing capability at Flat Panel Fabs can be adapted to a wide variety of MEMS devices. And here I've identified some of the development steps and concerns that might need to be addressed and could provide a starting point for a conversation between a product developer and a flat panel foundry. So if you are interested in this topic, my contact information is there. This includes design for volume manufacturing for Flat Panel Fabs or others. You can also find more information at Ann Fitzgerald's website. And also, if you're a MEMS designer who has experience bringing a MEMS device to a flat panel fab, I'd love to hear from you. Please reach out. I'm looking for more case studies, trying to gather data. I've already had some nice conversations, so that's been great. Yeah, so next Robert will give his perspective as a flat panel engineer.
All right, so my name is Robert Rodriguez, and I'm here to give part two, a Flat Panel Fabs perspective with respect to expanding the world of MEMS through Flat Panel Fabs. So to kind of emphasize what Kim was mentioning about bringing down the cost of producing certain MEMS products on our glass, what I did was I just wanted to show an example here, and these are to scale. I took a 10 millimeter square sample and laid it out on our piece of glass, and I was able to get over 5,800 samples on our one piece of glass compared to that of 284 units estimated on an 8-inch wafer below, just to give people kind of an idea of what Kim was mentioning as far as bringing down the cost per product. So now on to dpiX here. So dpiX is a joint venture of 4 companies, Siemens, Philips, Thales, and Varix. We do about $50 to $100 million in annual revenue. We have about 125 employees, and we are the single source supplier of a $5 billion industry. We're based in Colorado, and we are the largest amorphous silicon Gen 4.5 facility here outside of Asia, and we have over 20 years of manufacturing and design experience. And the picture up to the top right shows our facility and office areas and what have you. Just to give you an idea, we're also the world-leading manufacturer of digital optical sensors for some of today's most innovative X-ray solutions in the medical, industrial, military, and security imaging businesses. I included a couple of pictures of some samples of our photosensors arrays that have been converted into X-ray detectors. So this picture here shows a picture of the human skull, and you can see some of the veins, blood flow. And then the picture next is just the chest X-ray. So a little bit about history of dpiX. So dpiX actually has its origin here in California at Xerox PARC in the 70s, where the charter was to create the Office of the Future and the Architects of Information. So during the 1990s, dpiX was started to make cockpit LCDs. However, the same technology was determined that it could be used for X-ray imager technology. And so it started in Palo Alto, California. Eventually, we started to outgrow the substrate size in Palo Alto, which is Gen 2.5, which was 460 by 365. So we purchased a building in Colorado Springs, and we expanded and increased our size glass to Gen 4.5, which is 730 millimeters by 920 millimeters. The building renovation, qualification, process of development was completed in 2011, and we've been providing arrays to our customers ever since. And just to give you guys an idea, I took this picture. This is not normally what we would do in the fab, but you can see here 2 people holding our Gen 4.5 size glass. So the main takeaway from this slide really is just, we're home to 55,000 square feet of world-class clean room and manufacturing facility. We have vast experience with transitions from R&D to production volumes, working with our customers, as well as the ability of doing rapid product design and prototyping in our facility. We're 14001 certified, as well as 1345, which is an offshoot for for medical equipment makers. I won't go through the whole detail on this table below, but the main takeaway here is, as you can see, a lot of the equipment that we use to make our photosensor arrays is a lot of the same equipment that you would have in a foundry for MEMS. However, it's suited for glass as opposed to silicon wafers. Our technology offerings. So we have world-class photosensor arrays that enable the next generation capabilities. We have patented proven amorphous silicon thin film transistor technology, and we are in the process of developing an indium gallium zinc oxide TFT that has 10 times higher mobility compared to that of amorphous silicon. We also are very good when it comes to integration of amorphous silicon photodiodes with backplanes. Substrates typically use flat panel display glass. Our thicknesses are about 0.7 millimeters, although we are qualifying 0.5 millimeters on our fab to be able to work with other customers that need a thinner glass. And just recently, we've developed a polyimide process where we coat the polyimide on our glass and do the curing process, and then we apply the same process that we would use to make our photodiode sensor arrays on polyimides just as we would on glass. Our experiences with backplane architectures include active TFT, of course, and passive non-TFT. This is one of our larger arrays of our polyimide. This is a complete photosensor array. And then this is one of our arrays on glass. And actually, this actually has an organic photodiode material. So the next couple of slides, I'll try to give some examples of maybe some of the applications we can provide MEMS developers. So at dpiX, we specialize in depositing thicker, thin films. Our films are typically thicker than what you would normally see in a flat panel display company. This is a topside picture of our photodiode and our TFT. And then this is a cartoon cross-section to kind of show the differences of the films that we lay down. So as you can see here, these are relatively thin films for our TFT, but our amorphous silicon diode is fairly thick, as well as these are our interlayer dielectric layers as well. So these are definitely thicker than what you would normally see for a flat panel display company. And then also, this is just a sample of some of the designs that we have laid out for various applications. The other thing is that we also have the ability to test samples while they are still intact on our piece of glass. To the right, you can see some of the development arrays that we're doing with IGZO, where in this case we have 24 samples on our piece of glass, and they've all been tested. And the importance of this is that we can test them while they're still in the glass. We can take them to the laser, and then we can do repair, and then come back and retest them to make sure they're passing the specifications. And sort of this gradation is our tab pad. You're getting all the sensitivities from the tab pad test. We also have the ability to perform cross-section analysis in-house. Below here is one of our cross-section of our flex material. So here's our polyimide, which is on the order of about 14 microns thick. We have a buffer, TFT, and some of the thicker layers that I mentioned for our interlayer dielectric and our top metal. So in conclusions, to stress what Kim was saying, for some MEMS applications, dpiX can offer more samples on glass substrates, lower cost than on silicon wafers. We go beyond the limits of conventional imaging while maintaining high reliability and cost effectiveness. We have proven and patented amorphous silicon technology and world-class optical photosensors. dpiX offers many of the films and metals that are used for MEMS applications. We do many customizable arrays for customer-specific and demanding needs. We are the largest fab outside of Asia with over 20 years of manufacturing and design experience. We are located here in Colorado, and we have an IP-secure environment. And we have a world-class clean room and manufacturing facility with state-of-the-art tools and testing equipment. Thank you.
Thanks, Kim and Robert. I'm going to allow one question, if there is any. In the back there, Dee, you see?
Just one.
Well, we're running over, and I want to get to the next break.
That's the one where the fear is.
They're laughing, but they know what I'm talking about.
Applied materials. This is more for Kim. In the slide where you showed the comparison of the cost for 6 and 8 inch and compared to your 4.5 gen glass, where does 300 millimeter silicon stand in that comparison, or does it even make sense for customers to look at that?
So, I don't know if this is on. You can say it. Okay.
Welcome. Use my mic.
So, I didn't include 300 millimeter wafers because I haven't heard of a MEMS process that used the 300 millimeter wafer. I might be wrong, but that seems outside of what I might expect for a standard silicon process for MEMS. If I were to include that, if somehow I could get access to a 300 millimeter fab, then it would move down probably past that gap. But just in general, I wanted to show what would be available for a MEMS product developer.
Anyone with a half of a question? Well, there's a couple questions. Okay, let's go. Thanks, Tim.
Okay. What about mechanical property? You mentioned mechanical properties are a concern, but what about control, measurement, all of that good stuff, and can you achieve what you need to achieve? I'm sorry if it's not a half a question.
That's okay, it's okay.
I wanted to know.
Yeah. So,
Is this addressed to me or to Kim?
Both, I guess Kim, because you would have evaluated it.
so one of the really interesting things that I found when talking with Robert was when we're talking about displays, a dead pixel is a real problem. So dpiX and I suppose most flat panel fabs have the ability to fix dead pixels, which means they can address individual devices and increase yield in that way.
And we also, I mean, from the standpoint of process control, we make a lot of effort to prep the surfaces by cleaning them before they get deposition. There's inspection steps to make sure that the defects are not going to be damaging or destroying the pixels. If they do, typically we detect that in lithography, so then we can rework them. So we take a lot of pains to make sure our defectivity rate is quite low.
Half question. Are you working on glass interposers as you are working on some glass substrate?
We are not currently working on it. We have made proposals to work with people to do that, and we're still very much interested in doing that.
Okay, thank you.
I think there was one more.
Real quick question.
Thanks for the presentation. You know, if you were to do actual sensors on glass panels, how would you dice them? You know, dicing sensors is actually a pretty big challenge sometimes, and yeah, I'm just curious.
Yeah, so working with Kim, you know, we were not looking to dice the individual sensors. I mean, we have to do that currently with our photosensor arrays because they vary in size. So we typically do a mechanical dicing. But we're qualifying a laser tool that can have a lot more control and a lot better ability to cut different shapes, including cutting wafers. That is definitely an issue. I mean, as far as cutting, I don't think our factory, I think they would probably go crazy if we had to cut that many samples individually. But I think addressing what Kim is saying, there's a lot of back-end processing that might be needed. So we can certainly cut them down to what would be needed for the back-end processing.
Talked to Kim and Robert during the break. I can testify this is definitely in the future of MEMS. You can make amazing MEMS on large glass panels, and it's really fun.
Sorry, I have one more question. This is on, yeah. Did you find that the spraying, you mentioned wet spraying might be an issue. for MEMS. What did you find out about that when you looked at the tool set at dpiX?
Well, from my perspective, you know, a wafer, a silicon wafer, will go through some pretty aggressive processing, sometimes spraying, spin operations. But generally, if we have more delicate structures, then we might move to less aggressive techniques. But for a panel, going through a process like the one at dpiX, you might not be able to avoid this sort of high-pressure spray. So that's just something to keep in mind, and it could just mean that the back-end processing that would require the smaller panels might have to happen earlier in the process. But it's just something to keep in mind. It's not necessarily a deal breaker, but it could potentially damage some devices.
Okay, I'm cutting you guys off now.